In this video, I will show you how to build a precise servo motor control system using an ATmega328P microcontroller. We will cover everything from power regulation and oscillator stability to interfacing a 16x2 LCD and a servo motor. We begin by creating the reset circuit for the ATmega328P. I'm connecting a 10 kilo ohm resistor from the reset pin to the 5 volt VCC rail to keep the microcontroller running stably. A momentary push button is added to pull this pin to ground, allowing us to manually restart the program whenever necessary. Next, we build the power stage using the LM7805 regulator to step down our 12 volt battery source to a steady 5 volts. At the input, I am using a 100 microfarad electrolytic capacitor to handle large voltage ripples, alongside a 0.33 microfarad ceramic capacitor to filter out high frequency noise. At the output, we have a 10 microfarad capacitor for load stability and a 0.1 microfarad capacitor to ensure a clean, noise-free 5 volt supply. These capacitors are essential to prevent regulator oscillation and protect the ATmega328P from power spikes. To provide a precise heartbeat for our code, we now build the crystal oscillator circuit. We are using a 16 MHz external crystal connected across pins 9 and 10. To help the crystal start up and maintain a stable frequency, I am adding two 22 picofarad ceramic load capacitors connected from each crystal leg to ground. With the clock set, we connect the primary power pins of the ATmega328P. We connect VCC and AVCC to our 5 volt rail, while ensuring GND is tied to the common ground. Connecting AVCC is vital as it powers the internal digital circuitry for several ports, even if the ADC is not in use. Now, we interface the 16x2 LCD using a 4-bit mode to save pins. Data line the D4 through D7 connect to pins PCC through PC0. The RS and E pins are tied to PC5 and PC4. We also include a 10 kilo resistor potentiometer connected to the VEE pin for manual contrast adjustment. For user control, we connect the CW and ZCW switches. Each switch uses a 4.7K ohm pull-up resistor to keep the signal high when not pressed. Between the switches and the 74HC14 Schmidt-Trigger inverters, I've added an RC filter consisting of a 470K ohm resistor, 1 microfarad capacitor. This combination filters out mechanical switch bounce and electrical noise, ensuring the inverter delivers a perfectly clean logic signal to pins PB0 and PB1. The PWM control signal is generated on pin PB2 OC1B. We pass this signal through an LM358 op-amp configured as a voltage follower buffer. This protects the MCU and ensures the servo receives a strong, consistent control pulse. prevent system resets caused by motor noise, I am placing a large 470 microfarad electrolytic capacitor directly across the power and ground pins of the servo motor. This acts as a reservoir to handle the high current demands of the servo during movement. Finally, we start the simulation. On boot up, the LCD displays a servo control welcome message for 2 seconds. Once the main loop starts, you can see the LCD updating the angle, percentage and a visual door graph as I use the switches to rotate the motor. Is the exact text you asked me to reproduce, written out faithfully. That's it. This is how you can switches to control servo motor with PWM signal from ATmega328P. Thanks for watching. See you in the next.